Welcome back. So today we're going to dive deeper into RNA-Seq analysis using the output of the DE-Seq2 package. So this is following on from what we did last week. Today there won't be any slides. It's all just going to be coding. So to quickly remind you again, if you've set up a project for this meetup, that's great. Open up that project. And if you haven't, again, that's fine. Just open up our studio. So once again, we will need to reinstall the package that we've been using for this meetup. And it's using the install GitHub function from the remote package. So you type this and then ucct/cbrg, and you remember to specify that force is equal to true. Once again, the reason we're doing this every week is because this package is being updated weekly. All right. And then once you've done that, you can just load the package with using the library command. And so there are no slides for this week, so we won't be using the launch_slides function. We'll just be doing opening up the project RMD for today. Now, you can see here that I've put in library CBRG, but just to be kind of explicit, when I use a function from this package, I'm going to specify the name of the package and then 2 colons following that. Now, this is redundant, but if you want to err on the side of caution, writing out functions like this is a good idea. And we do launch project, and it's number 4, so we can do that here. And you should have the corresponding R markdown file. Let me just adjust this size. One thing that I didn't state last time, or rather restate, was if you make changes to this, with your own annotations and things like that, don't just save as you would, because it's going to save in the directory that has this package. What you want to do is you want to save as. So for example, let me make a minor change here. Put my name in. The best thing is to do save as. Sorry, it's a little tedious, but then, you just navigate to your project directory, and then you save there, and then you'll see it appear here. So you're making a mistake if you click save, if you hit save and you don't see anything pop up here. All right.
So if you had saved it originally, you would save to the directory still on our laptop.
Still on your computer. And I guess that's fine, but the next time you reinstall this package, it'll overwrite that. So I'm sure there's a clever way to just do it automatically. Haven't figured that out. So this is slightly involved. Now, the setup page, chunk here has all the packages you need. And these are 2 nice functions, again, written by Paul, that will see if you have the packages or not, and then install the ones that you don't have. Again, as is usually the case, this is the most error-prone part. So I apologize for any technical difficulties people might be having. But again, if there are any issues, please email us. So as you can see, there's a lot going on. Just keep an eye on your console, because they'll occasionally ask you for questions. So mine was fine here, and it's loaded the packages we need today. And so for today's kind of code walkthrough, we relied heavily on the DE-Seq2 and biomaRt vignettes. Now, DE-Seq2 is the package that we use to do RNA-Seq analysis. biomaRt is another package from Bioconductor that allows you to do things like, for example, there was a question last week. You have ensemble IDs. How do you get gene names or Entrez IDs or any other relevant information? biomaRt is a package that allows you to do that. The second chunk here is, again, there's a bunch of code. Now, this just effectively summarizes everything we did last week. And it's loading the necessary count and column data, producing this DDS, this DE-Seq dataset object, running differential expression analysis, and then saving it as a results table called res. So again, without going into the details of what these steps are, because that was last week. We just run all of it, and it should be it should work without any issues. All right. So now it's a deeper dive into this output. So for example, one useful function from DSeq to the DSeq2 package is this thing called mcalls. So if you just run that mcalls on your results table, you get this results table has multiple columns. And last week we briefly spoke about what the columns meant. But if you wanted to see exactly a description for each of these columns, you could run this mcalls function. Now, unfortunately, the way it's output here, you see that the descriptions are cut off. So if you wanted to see the descriptions just by themselves, you could run this mcalls on this res object and then use $description. And then you see that you can see the full things here. So this is just a handy little function to remind yourself of what these columns in your results table mean. So today, we'll mostly just be doing data visualization today. So one thing that is often done with omics data is to do principal component analysis. And so briefly, I assume people watching this are familiar with PCA. PCA has many, can be used for many things, but one thing from a data visualization perspective is to project this high dimensional data, which is impossible to picture onto lower dimensions, so 2 or 3 dimensions, so you can actually see your data points. Now, typically for PCA, if you wanted to do PCA in R, there are a few steps. It's not hugely complicated. It's just a few lines of code. But for these data, the DESeq2 package makes available just one function called plot PCA. So it's really simple. One caveat, you cannot apply PCA directly to your read count data for 2 reasons. One, it's not normalized. And we spoke last week about the importance of normalizing read count data to take into account things like differences in library size, sequencing depth, things like that. So this R-log transformation does a few things. One is it does this normalization step, but there's another problem with count data, especially RNA-Seq count data, and that is to do with this mean variance relationship. Now, with, for example, microarray data, I believe the assumption there is the variance across the genes is approximately similar, and that's great for PCA. But for count data, for RNA-Seq count data, the variance is proportional to the absolute count data. So genes that just happen to have a high read count, normalized read count, will also have a high variance. And this is not the kind of variance you're interested in, because the variance we're interested in is to do with biological effects. Like, did your drug really increase gene expression? Not to do with this kind of quirk of count data. And also I said that the mean was proportional to the variance. That's not exactly true for RNA-Seq data. It's actually the higher the absolute count, the variance goes up kind of exponentially. So it's called over dispersion. Anyway, that's a lot of stuff that needs to be accounted for. The good thing is this R-log transformation function takes care of all of that. So we apply it to our DESeq2 object, which we created here on line 70, and we just called it DDS. And again, if some of this stuff is unfamiliar to you, this is covered in greater depth in the previous meetup. So we have this. So RLD is like DDS, except these are now normalized counts, and the mean variance relationship has been corrected so that we can do PCA. So running PCA should be straightforward. I get a, oh, sorry. there's an error here. So with if you just run plot PCA like this, it says the argument int group should specify columns of call data DDS. Okay, so let's try to understand what this means. So it's saying that you need something from call data DDS. So just to remind you what this call data function does, if we run it on DDS, we get to see these information about our different samples. In this case, we have 6 samples. Now, int group stands for interesting group. So what this plot PCA function is asking for, it's asking you, can you give me some group information, some information about these samples so that I can put them in groups? Now, if we look here, of these 4 columns, there's only one interesting group, and that's this condition here. Because so that's, if we put cell, we'd have them all colored the same because they're all cell 1, or type, they're all epithelial. So if we go back here, and for the plot PCA, we just do int group equal to condition. Oops. To get something. Oops. Sorry, this is the thing that Paul brought up. This the plot comes up at the end of the chunk. So rather than scroll all the way down, and this is something that you can change the setting in RStudio, I just haven't. You can just run it in your console if you want to see it appear here. But here you get a nice PCA plot. You have really nice separation of your mock samples from your knockdown samples. It's kind of just because of the weirdness of this projector, you can't. Some of these points are cut off, but on your computer you should see 3 mock points and 3 knockdown points on that are nicely separated on this PCA plot. So that's not the only thing you can do with this new RLD object. You can also use it to make heat maps. One heat map you can make is a heat map of your samples. So in this case, we have the samples the metric you can use multiple metrics. The metric that is used for in the DE-Seq2 vignette is to work out the Euclidean distances between each sample from every other sample. So the Euclidean distance is just the Pythagoras formula, except instead of having 2 dimensions, you now have thousands of dimensions that equal the number of genes you are measuring. So there's a little bit, so the first thing you need to do is work out the Euclidean distances of the samples from each other. And to do that, you can use this function called dist. Now the thing about dist is, if we look up its documentation, $dist, it works out the distances between the rows of a data matrix. Now, if you look at your RLD, the normalized count data in your RLD object, as we discussed last week, the way to do that is to use this assay function. So if we do assay RLD, you get a lot. Have to scroll all the way back up. Oh, wow. So that was too big. Let me try the same thing. And then what you can do is you can view the output so that it comes up here. This way you don't have to scroll all the way down. So in this case, it's going to work out the distances. So this dist function, as it says, it works out the distances between rows. Here, if you just applied it naively to your assay RLD output, you would end up working out the distances between genes, which is it's not what you want to do. You want to do the distances between samples. So to do that, you can use this little function here. So there's a lot of nesting here called T, and T just stands for transpose. So it'll convert here, it'll make the rows columns and columns rows. So to view that, do the same thing, but put the transpose function. Take a little while to run. Maybe more than a little while. Anyway, while it's thinking about this, basically you just flip the columns and the rows. See? So now when you calculate the distances between the rows, you're calculating the distances between your samples, which is what we want. And so if we do all of this, we can save the output that I showed. Well, actually, no. We can save these distances as a new object called sample dists. And if we run sample dists, just to see it clearly, in our console, we see that we get the Euclidean distances between various samples. And this output here, the way dist works is it doesn't show the distance between a sample to itself. It just shows you, so for example, sample 1, it's unclear here, but sample 1, 2, and 3 are the mock, and sample 4, 5, and 6 are the knockdown. So you expect sample 1 to be pretty similar to sample 2 and 3. And so you can see the distance is quite low. Like to sample 1 to 2 is this 24, sample 1 to 3 is 21. But then when you look at the knockdowns, when you compare it to the knockdown samples, you see the distance increases. So this is a pretty good metric to use for our heat map. Now, there are various ways we can make our heat map. We could use ggplot. I just find that ggplot is a little limited for my needs, at least. And there's quite a lot to do to make more elaborate plots. Like to make a simple heat map is straightforward. To do anything more requires quite a bit of work. Fortunately, there are many alternative packages that are dedicated just to making heat maps. One really nice one is this package called Complex Heat Map that I particularly like. However, I'm going to use this P heat map, and so you just run library P heat map, and the P stands for pretty. And one of the reasons I used it really is because this is the package that they use in the walkthrough. Actually, I'm going to, sorry for the switch. It's just because there's quite a bit of code here, and rather than typing it all out, I'd rather just describe it. So what I'm going to do is I'm actually just going to cheat. I'm going to launch my project, but I'm going to show the answers. Sure, why not? Okay. So we are at this step here. Sample dists. We loaded a heat map, P heat map package. Now the first thing you need to do is convert it to a matrix. Now the reason you do that is that's what this package is expecting. So to convert something to a matrix, you can use this function called as.matrix. Pretty self-explanatory. But there is an interesting thing that happens here. So just to remind you, this is what your sample dists looks like. But if you converted it to a matrix, it takes a second, and you ran this again just in your console so that we can see it easily. You can see it looks a little bit different. So this is kind of a fleshed out version of the previous object you saw. So here you can see across the diagonal, they're all zeros because obviously a sample is identical to itself. Couple of other things we need for this. So right now the row names of the names of each of these samples are sample 1, 2, 3, 4. It might be nice on your heat map, instead of just showing samples 1, 2, 3, 4, to show 3 mocks and 3 knockdowns. Because sample 1, 2, 3 doesn't really convey that much information. So one quick way to do it is to the sample dist matrix object is to change the row names. So right now you can see the row names are samples 1 to 6. And we can change those to be mock, 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 knockdown, knockdown, knockdown. So to do that is we can run this line here, 106. Now you could kind of hard code this by just typing in combine and then mock, comma, mock, and so on. This is not a great way to do it. Or you can use, you can just do DDS $condition, And if we run this here in the console just to see what that looks like, we get this, mark, 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 knockdown, knockdown, knockdown. We can assign this to the row names of sample dist matrix. We run that here. And now when we run sample dist matrix, there's a nice shortcut here that you might not be aware of. On a Mac, if you do command arrow up, you can actually see all the things that you run previously. So this is nice if you don't want to type out stuff. So if we look at sample dist matrix again, we now see that we've changed the row names. And oops. Okay, so right now our matrix object has row names and it has column names. So if you just plot the heat map of this as is, you will get on your heat map, you'll see the sample 1, sample 2, sample 3. Maybe you don't want to see that. So to get rid of all of your column names, you can do something similar, except instead of using row names, you use column names. And to specify that you want to erase all the column names, you can just assign this null value to everything. We do it like this. So now if we run this, we see that it's erased all the column names. So those are all the things you have to do to get an object that you can now use for this pHeatMap function. So this pHeatMap package, its main function is also called pHeatMap. And if we just run that, actually, once again, let me just copy paste it into the console. We run that, we get a nice heat map. Pretty good. And it shows you that the mock samples are all neatly clustered together and the knockdown samples are clustered there. So this is a nice diagnostic step, especially when you have real life data that isn't so well separated. All right, so that's making a heat map using the pretty heat map package on your samples. What is a lot more interesting is making a heat map using your on the genes. So for that, we could either just make a heat map on all the genes, which would be super busy, or we can make a heat map on the subset of on an interesting subset of genes. Now, one way to define what's interesting for genes is to pick the genes that have the highest variance. Because if everything is similar to everything else, that's not very interesting. But if there's quite a bit of variance, then maybe that's indicative of some kind of biological effect. So to do that, again, we could work out the variance for each gene using dplyr, but that is actually surprisingly challenging and non-intuitive because dplyr doesn't really work so well row-wise, and there have been recent developments to improve that. But even those developments, I mean, they are pretty intuitive, but they don't work very fast. So when you apply it to genome scale data, those functions can really slow down. So for that, we will again rely on some BaseR approaches. So again, here a nice package that we will use to work out the variances of the genes is this package called GeneFilter. And GeneFilter, so we just run that there. GeneFilter has a bunch of really useful functions. One really useful function that we will use is this thing called row_vars, and that works out the variance of the rows. So to find, in this case, let's say we want to make a heat map of the 20 most variable genes in our data set, we can just easily run this line of code 120 here. I say easy because it's succinct, but there's quite a bit going on here. So to try to understand what all of this, oops, for some reason I can't adjust. Oh, I can. To try to understand what all of this means, the easiest way is to work inside out. So again, just to remind you, if so the innermost part is this function here, assay, this piece of code here, assay RLD. So I won't run this here, but this is the one that shows you the normalized count data for your experiment. You use this as input for this row_vars function. So now if we go to the next step up, if we just do row vars on this, it'll work out the variances for each gene. And actually, if I copy paste that and just run it as is, it might give me, it just gives you for each gene, it gives you the variance. All right. What you can then do is, so the next line up is to apply this function called order on these genes, on these variances. And we set this additional parameter to decreasing equals true. Just give me a second. So what order does if you don't set decreasing equals true? So when you did this row vars, you now have this long list of variances. When you apply order to this, these different variances, order will just say, we'll go through them, and it will say, it will work out the order of those variances. So if you have, let's make it simple. If you had three variances, 20, 50, 30, and you applied order to that, you would get 1, 3, 2. Because 20 is the lowest, 50 is the highest, and 30 is somewhere in between. So it gives you the rank. That's what I'm looking for, the rank of the variances. If you said decreasing equals to true, it will, so by default, order will order from the lowest variance to the highest variance. If you said decreasing equals true, it'll just flip that. And after doing all of that, if you just want the top 20 most varying genes, again in decreasing order, you can then go to the highest level and apply this head function. And if we run all of this here, these 20 numbers are the row indices of the genes that vary the most. And we can save all of that as an object called top var genes. So there's a question here, what do the numbers in top var genes mean? And like I said, those are the indices or locations of the rows that correspond to the genes that vary the most. In this case, the top 20 genes. Now you have all of that information, what can you do with it? So you can go back to your normalized count data, which you can access using this assay RLD here. And using the familiar square bracket notation in R, you can select the rows that correspond to these indices. So what this line of code here does is, and obviously you want all the columns, so on the right-hand side of the comma, you just leave that blank. So what this does here is it picks the rows specified by top var genes. And by definition, based on the code that you've run right now, those are the 20 most variable genes. So if we run all of this and assign it to this object called math, we just run that in our console, we can see we have now this matrix of 20 genes and 6 samples. And these 20 genes are the 20 most highly varying genes in descending order. So this one up here is the most variable gene in our data set. All right, so that was a lot of work to get this smaller, more interesting subset of genes. And in the vignette, rather than just go ahead and make a heat map for these genes, they make the argument that it's more interesting not just to look at the absolute variances, but to look at the variances to see how the gene expressions, see how much they deviate from the mean. So we can mean center our variances by just running this line here. So just as we had this row var function, we have a row means function. And to subtract the mean of each row from the corresponding elements of our matrix, it's really easy. You just do mat minus row means mat. And yeah, that's that. I'm actually going to pause here. Are there any questions? Okay, so now we have this mat thing, and we could actually, I'm going to actually just go ahead and skip to this line here. I'm going to type in p heat map because now this mat object is ready to make a heat map, ready to use in this p heat map function. And if we run that in our console, we get this heat map here, which again, it's crunched up, but it's actually not a bad plot. And so we can see we have the heat map of our genes. The pretty heat map function is a lot more powerful than this, and it allows you to do things. So doing something like this in ggplot, I think would still be a little bit challenging, but not hugely so. But we can embellish this plot more easily using this pheatmap package. And so one way to do that is, so if we go to this line 132, let me just run through this code and show you what the point of this is. So I ran through that and I created a data frame called anno, and we can use this anno to annotate our heat map. And so if you look at the pheatmap function, one of its parameters is this annotation underscore call equals. And if I actually just run that to show you what the previous lines of code did. Yikes. Sorry, that's just not formatting properly. Okay. All it did, that anno underscore call, is it allows you to annotate, in this case, your columns, so that previously you didn't have this here. So this kind of nicely shows you the 3 blue squares correspond to your knockdown and 3 pink ones correspond to your mock. And really, the only thing you need to get this is, if we look at the anno data frame that we made, is this one column data frame that has, so in this case, if you look at the annotation for your columns, you have a condition. So that corresponds to the column name. And the individual blue and pink rectangles correspond to the entries of condition. So mock, 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 knockdown, knockdown, knockdown. Essentially for this annotation data frame to work, the row names of this data frame have to be equal to the column names of the matrix. So if that stuff seems a little strange, I would encourage you to run this and play around with that to see how this annotation works. All right. So that is how to make a PCA plot, which is a little special when you're dealing with RNA-Seq data, and how to make heat maps using this pheatmap package. And again, like I said, if you don't want these fancy annotations, that's fine. It's hopefully I've demonstrated that it's pretty straightforward. You just need to have your genes as rows and your samples as columns. Make sure that they're a matrix, and then pass them through pheatmap. Right. The next one is to make a volcano plot. And for this, we will thankfully be moving back to familiar ggplot territory. So I just want to show you how kind of straightforward it is to make a fairly decent looking volcano plot. So as you know, for ggplot, we now need to move away from these S4 objects and matrices and things like that. We need a data frame. So to do that, this is a line from last week. We can convert our results object, this res object, into a data frame by using this as_tibble function. The only thing is we have to specify that the row names equal, you can call it whatever you want, but since these are ensemble IDs, we call them row name equal ensemble. If we forget to do this, we will get a data frame, but we lose all the row names, because row names are something that are not allowed in these special type of data frames, these tibbles. So by specifying row names equals ensemble, we just create a new column Now, if we look at resdf, instead of having row names as the ensemble IDs, we just have a dedicated column that contains the ensemble IDs. This is from last week. Again, we had a lot of missing values, NAs, for our adjusted p-values. So we can clean it up by using this drop NA function. So here I'm just going to overwrite this res_df object, which is up to you whether or not you want to do that. Now, to make a volcano plot, typically you have your log fold change on your x-axis, and you have your negative log 10 p-values on your y-axis, and that's to ensure that you get that nice erupting volcano look. So one way to do, so we can either just do this on the fly, or you can just make that dedicated negative log 10 p adjusted column in your data frame. And to do that, it's really straightforward. I'm not entirely sure if we explicitly covered it, but to make a new column in a data frame, you use this function called mutate. So again, we take our resdf data frame, and then we pipe it into this mutate function. And the mutate is super straightforward. You give it the name of the new column you want to make as the first entry, equals to something that you're doing to an existing column. So in this case, the existing column is p adjusted, and that something I'm doing is taking the negative log 10 of all its values. Now, one pretty simple mistake you can make is just do negative log, assuming that it's negative log 10. It's not negative log 10. In R, this log by itself is a natural log. So log 10 specifies it's negative log 10. And if we run this and look at resdf again, we now see that we have a negative log 10 p adjusted column. And by default, mutate, any columns made using mutate always appear at the end of the data frame. Okay, so we now have our log 2 fold changes. We have our negative log 10 p adjusted p values. Now, there's another thing that we can do here. And this is if you wanted to, it's nice to be able to see, to highlight points in your data, in your volcano plot that are interesting. And by that, interesting is up to you to define what that means. A lot of people take that to mean, well, it should be less than an adjusted p-value of 0.05 and above some absolute fold change. So here's one way to kind of quickly make a plot that highlights those points. We can again make a new column. So in this case, again, use a mutate function. We can call this column significant. And this is just a Boolean column. So if the the data point matches this condition here, meaning it's significant and it's above a certain threshold, in this case I've said above 1, the absolute log 2 fold change, it'll be true. It'll contain a value of true. If it doesn't meet this condition, it'll contain a value of false. That's it. So we just do that. And then if we look at resdf, again, scrolling all the way to the end, we now have a significant column that just says, is this particular comparison significant or not? All right, so that's a lot to prepare our data frame to now make our volcano plot. And to make the volcano plot, it is you take your data frame and then you pipe it into ggplot, and you want to specify that the log 2 fold change is your x-axis, and the y-axis is the negative log 10 adjusted p-value, and that's the variable you just made. Now, to get this color component, you can specify the color parameter to be equal to this new variable you created called significant. And this is kind of a clever thing, because what this tells ggplot to do is that based on, it'll color the true values. It'll give the true values a certain color. It'll give the false values a different color. And since we're making a scatter plot, we use geom point. And we can specify a certain size. And if you wanted to see what all of this looks like, you can just go ahead. Actually, you can just run this in the console, just the first 4 lines, and you get a nice heat map. One thing you can do with heat map, and it's typically done by people, is to highlight these boundaries, the p-value boundaries and the log fold change boundaries. And to do that, there are these dedicated functions in ggplot called geom hline and geom vline. So geom hline is for plotting horizontal lines. The H stands for horizontal, and V is vertical lines. And they both take in intercepts. So geom hline, since it's a horizontal line, you want to know what the y-intercept is. So in this case, we specify that the y-intercept is an adjusted p-value of 0.05. And since the y-axis is on a negative log 10 scale, you'd have to do negative log 10, 0.05. And then you would need 2 V lines to account for the negative log fold changes and the positive log fold changes. And since it's a V line, they intersect with the x-axis. So we have x-intercepts, in this case, -1 and +1. And if we run all of this, so again, we can just copy paste this into our console. We get this. And you can easily adjust the line type so that it's dashed or it has points. You can adjust the thickness, the color, things like that. And so this significant false true, if you wanted to get rid of that. So there's this function called theme. That's a very powerful function that allows you to adjust any element of your plot you want, of your plot that you want it to. But because of that, it has a lot of arguments. So one simple one is if you just want to get rid of the legend, you do legend.position is equal to none. And we will run all of this. We get this plot, which is pretty decent. Now, kind of as homework, or this is just something to think about. All of this stuff that I did, I made a lot of these kind of additional columns and to make this plot. Now, you can run all of that. Let's say you just wanted to keep your data frame pristine. You could run all of that using just these lines of code, 170 to 177. So this is a much, quote unquote, cleaner way of doing it. So I think it would be a good exercise to compare this with this code up here, and also confirm to yourself that this will give you exactly the same output. Questions about volcano plots? I have one question. Can you think of, I'm pretty sure this was covered previously, can you think of a quick way to get rid of the background, the gray background? One quick way is there are these plenty of these built-in theme functions that allow you to adjust the theme of a plot in general. So one nice one is this theme minimal. We run this. Oof. Oh, okay. This is instructive. This theme minimal, if you put it at the end, it's overriding the previous theme line. So to make sure that your legend position, you don't have a legend, you just need to change the order. And this should hopefully, yeah. So now you have a clean white background. What if I wanted to give this plot a title? What would I do? A couple of intuitively named functions that I can use to insert a title.
Text.
Text is a good guess. It's actually just title. So, my plot. A more useful one, so just to show that this works. Oh, I guess I don't know how title works. That's how title works, right?
GG title.
It's GG title?
Yeah.
Oh, so what is title?
Build base art, that's why you get that problem.
I
You
see.
need labs. So equals.
Okay, my mistake. So the other way is to just do labs, and actually labs is more powerful because you can do title equals my plot, but then you can also adjust other things. So these are actually pretty decently formatted. But if I wanted to, for example, change my y-axis to negative log 10, not really sure why I would actually want to do this, but just to show you, just do this. Now I have a title, and I have this extra long y-axis name. I thought title was, okay, so title is not a function, a ggplot function. Okay, so that's the different kinds of plots we wanted to cover that are relevant to RNA-Seq data. Now, for the final 10 minutes, I wanted to introduce you to this really useful package called biomaRt. And before I get into that, if you want to learn, so biomaRt is this comprehensive package that allows you to do all kinds of things, and we will really just be scratching the surface today. If you wanted to learn about all of those things, one way is to just Google biomaRt. But from within R, if you want to learn about any package, you can use this browse vignettes function. I'm not going to run it here, but if you were to run it, it would just open up a collection of vignettes in your browser window. And then you can either, actually, let me just do it. Right? And so in this case, there are two vignettes here. And it's pretty cool because you can either just look at the R code itself and follow along, or if you want something that's nicely formatted, you can click on the HTML. And you can see that it was updated pretty recently, which is always good to see. And everything you could possibly want to do with biomaRt. And then, yeah, there's much more detail. Okay, I take that back. The first vignette's more detailed. All right. So there are a few. So the kind of disadvantage of the negative aspect of using this new package is just learning the vocabulary that comes along with this new package, but it's designed in a pretty nice way. So we can split this into a few steps. So step one is to connect to a particular biomaRt database and a particular data set within that database. So biomaRt gives you access to multiple data sets and databases. So since we're interested in as input, we're going to use these ensemble gene IDs. We can use this function called useEnsemble. And within it, we just have to specify two things: the name of the database, the biomaRt. So we do biomaRt equals genes, and the data set, Homo sapiens _ gene _ ensemble. So we run all of this and we assign it to an object called ensemble. This step could take a little long because it's connecting to a database. So as you can see, it's running. Now, I'm not going to run these two functions here on lines 194 and 197. But in this case, I just said biomaRt is equal to genes, dataset is equal to 8 sapiens gene ensemble. How did I know that? One is I just Googled it. But if you didn't want to Google that, there are functions that list all the available databases, and within a chosen database, they list all the available data sets. So if you scroll through them, you can see, oh, I'm interested in gene information. So I'll pick the genes. So we can just run this here in our console. And, oops. And so we see here the first database is of biomaRt. It's called genes. But then they also have other databases on mouse strains, SNPs, regulation. For list datasets, unfortunately, it's a lot bigger. And if you look at the details of the list datasets function, they have some clever arguments you can put in. It's almost like regular expressions where you can look for, you can home in on what you're interested in. Because in this case, we have datasets that correspond to various species and things like that. But so there are plenty of datasets. Anyway, we're interested in this database and this specific dataset. Now, to get the to retrieve the information of interest, we use another function within biomaRt called getBM, and it takes on multiple arguments, but three valuable ones are: we need to specify this attributes argument, and this specifies what the output will look like. So if we do attributes equals, in this case, ensemble gene ID and external gene name, it will give us a data frame that contains two columns, one with the ensemble gene IDs and one with the external gene names. And you can make this as big as you want. You would have to look at the documentation to see, so for example, if you wanted a data frame with 3 columns, you would have another one, and I believe it's just called Entrez ID. But to see what the exact name is, so it's like gene name, it's not obvious to me that biomaRt uses this external gene name, but to know that that is in fact what you have to put in if you just want to get the gene names, the guide will have that information. So that's the columns you want to get. The second is the values you are using to query. So in this case, our input are these ensemble IDs. So it's pretty straightforward. You do values equals, and then to access those ensemble IDs, you just put in the name of the data frame, so res_df, and then $ensemble. And this mart equals ensemble is what you specified previously, which database and which data set you're using. And that's kind of it. And so if we save the output,
should be uppercase, actually.
Uppercase for
in ensemble.
Oh, good catch. Thanks, Paul. All right, so now if we look at gene names, let me just look at it here. We can see that we have a column of the ensemble gene IDs, and this corresponds to the ensemble gene IDs that are in this resdf data frame and the corresponding gene names. Now, one thing that is particularly problematic about gene names is missing values. So unfortunately, it's not obvious here, but if you just click on this, you see that there are a lot of ensemble gene IDs that don't have a corresponding gene name. I'm not quite sure why it is here, but there are various reasons. So one question, and the answer is here, I'm just hiding it, is how would you, what is one way to find out how many missing values you have in external gene name? Just give you a few seconds to just broadly think about what you would do. Any suggestions?
Is there a count function?
You could. Sorry. Yeah, that would be one way to do it. As Paul suggested, you could do gene names, pipe it into a function called count. And what are you counting? You're counting these external gene names. And just to get to the highest value, so in this case, I cheated. I know that the missing accounts for the highest number. You can pipe that into a function called a range, and then you do it in descending order of number, and you see the 21,637 missing values. So it's pretty concerning. But and just to prove that that is in fact the right answer, another way to do it is you can pipe gene names into a filter function, and then you do equals to, because it doesn't give you NA when it's missing, it's just blank. You can do equals to, and then just open quotation marks with nothing in them. And then there's this new function called, or new to us, called nrow. It just gives you the number of rows. And if you wanted to know the number of columns, you do ncol. So if you ran this, you would get the same answer as Paul, but the difference would be it would just give you one number. So if we ran that here, we just get that number. Okay, 3 minutes. The last thing I want to say is, now you have this gene names data frame, and you have your resdf data frame. Won't it be nice to combine them? And to do that, we have to use one of these functions, one of these many join functions. In this case, an appropriate one would be left join. And it's probably easiest, if you've never come across these functions, is I've inserted a link to these really nice animations that show you how they work. So in this case, we have two very simple data frames, X and Y. And both X and Y, so that's X here and Y here. X has 2 columns, Y has 2 columns. They both have only one column in common, and that's these numbers here. So if you do this left join, and here the order matters, X comma Y, the resulting data frame, which you will see appear in a second, looks like this. And the resulting data frame will have 3 columns. The column in common, all the rows of X, and only the rows in Y that have matching values in this number column. It's tricky to describe, but this animation shows what we're trying to do. So this is an appropriate join to use for our data. So again, I have, in this case, so here I'm just doing left join data frame 1 comma data frame 2. Here you can use the pipe notation to specify that res underscore df is the first data frame. You pipe that into left join, and the second data frame is called gene underscore names. Now in this case, we know that ensemble underscore gene underscore ID is equivalent to ensemble, as in they contain the same information, but they have different names. So to tell R that these are in fact referring to the same values, we can use this by equals argument. We wouldn't have to do, I mean, it would probably work it out anyway, but just to write problem-free code, you can specify by equals, and then we use this combine or concatenate function, and then we put the name of, so in this case, it will also give me an error because it should be this. That's the name of the column in the first data frame, resdf, and that's the name of the column in the second data frame that we want to join with. It's here. If we run these two, again, rather than describing it, if we just look at the output, we now see we have an external gene name column that corresponds to where the gene names correspond to the ensemble IDs. So that's all there is for today. So it's a lot of plotting and an introduction to this super useful biomaRt package. Next week, we're going to wrap up RNA-Seq analysis by doing different kinds of enrichment analyses. So this is like GoTerm enrichment analysis and gene set enrichment analysis. All right, thank you. Questions?